Okay, so we begin here with an example where we're asked to find out which function grows faster, f or g. Does ln of x or fourth root of x grow faster? Well, if you remember what I said earlier, ln of x is actually going to be outperformed by any power of x. So what we should see is that ln of x grows slower, so g grows faster. So if I set my limit up as x approaches infinity of ln of x over x to the 1/4, then what I should discover is that if ln grows slower, then this limit should go to 0. And if x to the 1/4 grows slower, then this limit would go to infinity. So of course, starting out, this is an infinity over infinity limit. So we apply L'Hopital's rule, take the derivative of each piece. And so derivative of ln is 1 over x. For x to the 1/4, we would multiply by the exponent, get 1/4 x to the negative 3/4, which I could rewrite as 1 over 4 x to the 3/4. Okay. And then remember that I could rewrite this as a multiplication problem. This thing divided by this thing would be the 1 over x times the reciprocal of that, and we would actually get this limit. Limit as x approaches infinity of 4x to the 3/4 up top over x on the bottom. And then this would simplify to be limit as x approaches infinity of 4 over x to the 1/4. And of course, as x goes to infinity, x to the 1/4 will still go to infinity. So we have 4 divided by infinity, which would be 0. And so it turns out the fourth root of x grows faster than ln of x. Fourth root of x grows faster than ln of x. Okay. Our next example, we look at f of x equals x to the 400. And then g of x equals e to the x. We want to compare these two functions. So again, take one or the other and put it on top. I'm just going to do them in the order because again, if it goes to 0, I know the bottom will grow faster. If it goes to infinity, I know the top grows faster. So here I have an infinity over infinity once again. So I would take the derivative. That would give me 400x to the 399 over e to the x. That would again be an infinity over infinity. So I'd take the derivative again, and again, and again, and again. Okay, until eventually I end up with this. 400 times 399 times 398 and so on times 3 times 2 times 1 right on the top. It's a really, really, really big number. And in the bottom, after I took the derivative of e to the x 400 times, I would have just e to the x still. So even though this is a massive number, it's still divided by infinity, so it still goes to 0. It still goes to 0, and so therefore e to the x grows faster than x to the 400. even though you're going to have to go pretty far out to the right to see that, because x to the 400 is going to dominate for a long time. But e to the x will outgrow it. E to the x will outgrow it if we go far enough. Okay. So I'm going to do one last example here. We already saw that ln of x grows slower than powers of x, like x to the 1/4. But what if we raise the ln to a power? In other words, we square the ln, make it grow faster by squaring. Once it gets past, once it gets to be bigger than 1, when you square something, you get a bigger answer. So would the square of the ln, would that be enough to grow faster than a power of x? And we're just going to do a simple power of x here, just x to the 1st. Okay, well, let's see what happens. Let's set up our limit. And again, I'm just going to do them in the order they're written down in. So my numerator is going to be ln of x squared over x. And of course, that's an infinity over infinity. All right, so we apply L'Hopital's rule. So we'll be doing the derivative of the ln of x squared. So to do the derivative of ln of x squared, we would multiply by the exponent, 2, and then that would be ln of x to the 1st, times the derivative of ln of x, which is 1 over x, and all of that will be over the derivative of x, which is 1. Okay, so this is actually still going to be an infinity over infinity situation again. We're going to have 2 ln of x on top, and 1 over x would put an x on the bottom. So it's still an infinity over infinity limit, so we do the derivative a second time of both the top and bottom. So this is going to be 2 over x over 1, and limit of 2 over x as x goes to infinity is going to be 0 over 1, which would just be 0. And so it turns out that the x there grows faster than ln of x squared. In fact, it'll actually grow faster than ln of x to any power. To any power, x to the 1st will still grow faster than that and outperform it. Okay. All right, so these are just a few examples here where we're able to compare functions by looking at their growth rates, or look at the growth rates of functions by comparing limits involving them. Of course, those are actually indeterminate, infinity over infinity limits that we're comparing, right, to see if one grows faster than another. And again, if you were to do this and get some non-zero number, then the two things that have comparable growth rates.